Hello, everyone, and thank you all for attending to my presentation. My name is Marcel Favereau, and I am a PhD student in engineering science at the Pontifical Catholic University of Chile. And today I will talk to you about our research multi-stage adaptive bus optimization for the management of electric resources, which is a joint work with my advisor, Álvaro. So let's begin talking about two important facts. The first one is related to the long-term goals that some countries have at this moment, such as carbon neutrality and the phase-out of coal power. And the second one is related to the emerging technologies in the electricity generation, where we can find some interesting technologies like CSP or green hydrogen that are changing a little bit the way we face the long-term goals due to their characteristics. But the question now is, what's the role of hydroelectricity in this deep decarbonization context? Well, hydroelectricity has some important advantages. It is affordable and reliable source of energy. It adds flexibility to power system operations because it allows the integration with other renewable energy sources. And additionally, it's a low carbon technology. But also it has some challenges, and these challenges are mainly related to climate change effects like water scarcity and the corresponding uncertainty. In Chile, we're facing a mega drought since the last 13 years, and water scarcity is a very important topic here. So the questions that, or the key questions here are mainly maybe two. One is how to smartly manage the hydroelectric resources and what would be the role of these resources in the medium and long term. And this work is mainly focused in the first one. If we review some literature about different topics related to this, the management of electric resources, we can divide it in different topics. Let me start with hydroinflows modeling, where actor-regressive models and vector-regressive models, periodic autoregressive models, and some other derivations have been commonly used in literature to model these hydroinflows. And these type of models are very interesting because they can cope, or they can be connected with optimization models because they preserve linearity and because they are additive models. So here are some examples, such as the spatiotemporal periodic autoregressive models, Lohmann, Herring, Rivenac, the robust optimization, the two-stage robust optimization paper of Dashti, Conejo-Yan, Wang, with a vector autoregressive model in the uncertainty set, and the comparison between a time series SDTB and Markov chain SDTB of Landolf and Shapiro for this problem. All of them based, obviously, in the seminal paper in some way, based in some way in the seminal paper of SDTB of Reyer and Pinto of the 1991. There are some other approaches, in particular some risk-averse approaches, like the works of Shapiro, De Caya, De Costa, and Suarez, Hamem de Mello, Pagnoncelli, which incorporates some risk-averse functionals to the objective functions and analyze their respective results. Another concept or methodology very interesting that has been incorporated in the management of water resources are linearization rules, where these two papers propose the utilization of linearization rules for reservoirs management, but in a fluid management context, not in a hydrothermal scheduling as we're facing here. So what are the main contributions of this research? First, we propose a multi-stage robust optimization model for the management of electric resources based on linearization rules, where hydroinflows are the uncertain components. We also consider a low-dimensional uncertainty set based on vector-regressive models in order to capture statistical characteristics such as transitionality and spatiotemporal correlations between hydroinflows. To efficiently solve the proposed optimization model, we restrict our decision variables to be affine functions of certain parameters using linearization rules. And additionally, we consider a particular type of affine policy, which is a full affine policy that we will discuss later in some slides after. We carried out additionally extensive computational experiments to demonstrate the benefits of the proposed model. The interesting part is that the problem can be solved for large-scale instances, that is, hundreds of hydronodes and connections, which avoid network simplifications and thus incorrect signals of the value of water. So let's talk about a little bit about the proposed model. Well, we are proposing here a multi-stage adaptive robust optimization model. And I don't want to get into deep detail about the mathematical formulations. The equations are here in the presentation. So if you have any question about that, we can review it at the end of the presentation. So basically, we want to minimize the worst case operational cost. And we have some additional constraints, some classical constraints of this problem, which are reservoir dynamics, flow balancing past nodes, because we're considering hydronodes and hydro connections or hydroarcs. And so we have basically a network here. We have linear approximations of seepages for reservoirs. We have energy balance constraints. Additionally, we are considering a DC power flow representation. So we have these equations of DC power flow as constraints. We have some variable bounds, obviously, some reservoirs terminating conditions in order to avoid to empty the reservoirs in the last stages. And finally, we have the nature of decision variables. And as you can see, all these variables are real. So we have a big LP problem, a linear programming problem. So okay. And as the proposed model is in an infinite dimensional function space, we will restrict our variables to the affine functions of the uncertainty. These affine policies that I told you before, or linear decision rules, which is the same. And we will analyze three different designs in terms of the affine policies considered and the uncertainty sets considered also. These are these three: Rufus Model 1 or RM1, Rufus Model 2 or RM2. The first consider an affine policy plus a static uncertainty set. The second one considers an affine policies also, but in this case, a dynamic uncertainty set. And finally, the robust model 3 or RM3 is a combination of the previous two configurations. So the robust model 1 or RM1 is inspired by the classical paper of Antal of 2004 of adjustable robust optimization, which consider a box uncertainty set centered at some nominal value alpha hat with some deviation factor theta. Additionally, we consider a full affine policy in the sense that decisions, the decision policy for each stage depends on the realization of the uncertainty up to that stage, which is the part of here in the affine policy. There is an interesting thing that this type of policy automatically satisfies non-anticipativity. Okay, and then the robust counterparts of this model can be obtained based on the reformulation of Antal, of the paper of Antal, which doesn't use duality-based techniques. It admits a direct reformulation. But the main difficulty is that it is too computationally difficult to solve because of the number of hydro inflows we are considering in our networks or representation, power system representation. We will discuss it later. So the RM2, due to the drawbacks of RM1, now we will review the RM2, right? Which has a different uncertainty sets. And this set is mainly inspired by a vector autoregressive model in these two constraints here, which can be considered as a dynamic uncertainty set of those similar of those presented in Rorkan-san 2014 and 2017. And additionally, the dimensionality of this uncertainty set has been strongly reduced using principal component analysis. So our uncertain component here is epsilon instead of alpha at this time. In here, we're considering a similar affine policy to RM1's, but with the difference that we now are considering the projection, these epsilon variables, of the hydrogen flow given by the PCA instead of the hydrogen flow, as I mentioned you before. This is completely promising because there exists a strong spatio-temporal correlation between hydrogen flows, and as this plot depicts, with less than 10 principal components, we can explain more than 99% of the original variance. In particular, with 3, 4, and 7 components, we can explain 93, 95, and 97.5% of the original variance. So this is a very promising result. However, and despite of the statistical intelligence of this uncertainty set, the adjustable robust counterpart of this RM2 doesn't admit a direct reformulation as in RM1, and duality-based techniques have to be used here. And this implies that the reformulation remains computationally expensive for large-scale instances. So now the question is how to combine the advantages of both models, RM1 for one part and RM2 for the other part, within the same optimization model. That's the difficulty. Now I will present the lastest model, the RM3. This model combines and incorporates some of the advantages of RM1 and RM2. In one hand, we are considering a bar representation, a vector regressive representation of the hydrogen flows, but the uncertain variable epsilon is contained in a box uncertainty set, as you can see here, centered at 0 with some absolute deviation gamma. Now, the values of gamma have to be carefully determined in order to avoid negative inflows. So it needs a special treatment that we can discuss later in the Q&A after the presentation. We are considering also these affine policies, the same as in RM2. In this plot, we can see an example of the uncertainty set with 4 principal components for a random hydrogen flow. The most interesting fact of this last formulation is that the robust counterpart of RM3 can be obtained based on the reformulation of Ental, the same as in RM1, or very similar at least, without using duality-based techniques. And additionally, this RM3 incorporates the statistical intelligence of RM2, particularly the effectual regressive model. So, for the experiments, we will consider 3 different Chilean power system representations, namely the 8 bus, the 103 bus, and the 227 bus. However, it is very important to highlight the fact that the 3 representations consider the entire real hydraulic network, which consider hundreds of hydro connections and hundreds of hydronodes and the same quantity of reservoirs. Additionally, all the following experiments are implemented in the Julia language and solved with Gurobi 0.9 in a Intel Xeon CPU, an Intel Xeon server with 64 gigabytes of RAM. To analyze the 3 proposed models, we define a test system, which is the 8 bus instance, but instead of having 3 first stages, this test system has only 3 stages. And the solution times for the test systems, are 12 hours, 30 minutes, and 2 minutes for RM1, 2, and 3 respectively. Since RM3 is the most efficient, the following experiments will be carried out with this model, as we expected. In terms of the performance of the affine policy, we consider the original objective function, which is the WCM, worst case minimization, and a new one, which is the nominal case minimization, because the first doesn't show a significant improvement for different certain trajectories, which can be seen here in this column of WCM for delta equal 1 to delta equal 0. The total cost for the worst case trajectories or the nominal case trajectories, or even for the best case trajectories, is almost the same. But the worst case is almost the same, right? It only exists a difference of about 0.1% maybe, sorry. In all the cases, is very small. But if you can see the results of the minimization of the nominal case, there is a huge improvement between the worst case trajectory and the best case trajectory for this problem. So in the following experiments will all be based on the original multi-stage robust optimization model, but with this new objective function. So for the sensitivity analysis on the number of principal components, we will consider 3, 4, and 7 principal components, which represents an explanation of 93%, 95%, and 97.5% of the original variance. As we can see in the table, the solution times show an improvement growth when there are more principal components, which have sense because there will be more variables and constraints to add to our model, right? Additionally, and as explained earlier, a higher number of principal components doesn't mean that the uncertainty set is wider, neither that the worst case are even worse. So the worst case total cost for k equals 7, for example, is less than the worst case total cost for 3 and 4 principal components. In terms of the sensitivity analysis on the level of conservativeness, as we can see in the table, the value of delta doesn't have an impact in the solution time, which is expected since the number of variables and constraints remains the same, basically, regardless the value of delta. However, if delta increases, the total cost also increases because the worst cases are even worse and the system receives less water, basically. Also, it is interesting to note that the optimal solution of the robust model for delta equals 0, which is here, it means without uncertainty, is 1.83% less than the cost of the deterministic model. So this can be considered as the price for dimensionality reduction, or the price that we have to pay for the dimensionality reduction of the stochastic process, which is a very interesting concept. Finally, in this table, we can see the computational efficiency of the proposed model in terms of the size of the power system network. Recall that the 3 representations have the same hydraulic network. But the interesting issue here is that the problem can be efficiently solved for the 8 bus and the 103 bus representations. For the 227 bus representation, which is the most complex representation, it can be solved for 3 and 4 principal components. So in summary, on our best knowledge, this research presents is the first that approach this problem with a proposed multi-stage adaptive robust optimization model for the problem of hydrothermal scaling and solves a large-scale system instance for the same problem. So in summary, this paper proposes a multi-stage adaptive robust optimization model for the management of electric resources based on the use of affine policies. This model can deal with the uncertainty and spatial temporal correlations between hydroelectric flows of the entire hydroelectric network. The proposed model admits a direct reformulation without using duality-based techniques, which also makes it computationally efficient for large-scale power systems, as we saw in the results. And extensive computational experiments were carried out on the 3 representation of the Chile power system with up to 227 buses and hundreds of hydro nodes and connections, which is the most important thing, maybe. And some advantages of the proposed robust optimization model over stochastic optimization is the following: hydro uncertainty representation, because in robust optimization, the uncertainty is modeled directly within the optimization model, and it avoids the sampling process carried out by SO, stochastic optimization, which is related with the balance of the statistical representativeness of the stochastic processes and computational efficiency of the resulting optimization model. Additionally, model resolution. The proposed robust optimization model is efficiently solved without using algorithms or decomposition methods, which is an important fact here. The use of full affine policies considered in this robust optimization model automatically satisfy non-anticipativity, which is very important. And they provide the decision maker with an operational policy that adapts to any realization of the uncertain variable within the uncertain set. This is very, very interesting when we consider or when we think about decision makers. And finally, the incorporation of other uncertainty sources. Obviously, this paper is mainly focused on the management of water with it as a source of uncertainty. However, other sources of uncertainty can be easily incorporated. And in fact, this is another of the main advantages of robust optimization over traditional stochastic optimization. So future efforts, I think, that have to be guided in that direction. So that's my presentation, and thank you all for attending to this.